Greetings. Good days to you, global citizens. My name is Dr. Evans Lee. I write to fellow designers, entrepreneurs, investors, and visionaries who are exploring industrial applications of plasma technology and seeking new pathways to transform materials processing at a global scale. Over the past years, I have had the opportunity to design and operate a high-power arc plasma smelting system based on a 700 kilowatts, 22,500 volt direct current arc plasma configuration. This system was successfully deployed in Republic of Korea, where platinum group metal-bearing ores were directly smelted using plasma energy. Unlike conventional batch melting processes, the system was engineered for continuous smelting operation, enabling a designed processing capacity of up to 10 tons per day. The furnace was operated in campaigns of approximately 20 continuous days per month, demonstrating the capability to process roughly 200 tons of feed material within a single operational period and produce concentration-enriched PGM ingots. While large-scale commercial production still requires further investment and expansion, the technical feasibility has already been validated. The project progressed beyond laboratory experimentation into pilot industrial operation, including plant construction, system optimization, demonstration campaigns, and the successful production and sale of approximately 100 kilograms of PGM ingots. This experience confirmed not only the scientific validity of plasma smelting, but also its practical industrial potential. Building upon these results, my current focus is the design of a fully robotic, mobile, and modular plasma smelting system. The objective is to create scalable metallurgical platforms that can be deployed rapidly, operate autonomously, and dramatically reduce infrastructure constraints traditionally associated with high-temperature refining facilities. With the collaboration and support of entrepreneurs and investors around the world, this technology has the potential to fundamentally change how critical metals are produced. Without relying on chemical reagents and avoiding the environmental burdens of conventional hydrometallurgical processes, plasma smelting may enable production rates that are at least 10 times, and potentially up to 100 times, greater within the same operational time frame for platinum group metals and rare earth elements. To help a broader audience understand the scientific and industrial foundations of this approach, I intend to introduce and explain the technology based on the principles presented in the Handbook of Thermal Plasma, making its possibilities accessible to engineers, investors, and curious minds alike. The material may appear highly technical at times. Nevertheless, I hope readers will revisit it more than once and find the process both rewarding and intellectually enjoyable as understanding deepens. If this vision resonates with you, I warmly invite your interest and communication. Contact Fabrics.of.Universes at gmail.com. Thank you for your time and curiosity. I hope you enjoyed the actual plasma torches in my plant and the operation videos in the preceding intro videos. Now, in this video, direct current and alternating current arc plasmas will be explained together as they share the same underlying physics, but alternating current polarity reversal at line frequency can mask the essentials. Part 1 of this video focuses on the arc column and the electrode regions. The Ellenbos-Heller model helps extract trends, including feasible maximum temperature versus power input. The Watson model provides a simple single-fluid description of arc column behavior, but not introduced here for simplicity. This part also separates cathode and anode regions and highlights different current attachment mechanisms. Part 2 shifts to the current voltage characteristics and electrical stability. The IV curve ties the operating point to stability and control choices. Stabilization options range from free-burning and self-stabilized arcs to gas, wall, vortex, electrode, and magnetic stabilization. Finally, integration into plasma devices such as arc gas heaters, plasma torches, and transferred arcs is treated as a dedicated follow-on topic. This slide sets the baseline for understanding the arc column and the electrode regions in a thermal arc. In the arc core, the plasma state generally approaches local thermodynamic equilibrium, meaning both kinetic and chemical equilibrium are reasonable approximations. The main departures from local thermodynamic equilibrium are expected at the arc fringes and in regions influenced by a cooled wall. When the arc operates in a high-intensity regime, the conditions commonly include currents above 100 amperes and pressures above 10 kilopascals. Under these conditions, the arc behaves closer to a thermal plasma in the classical sense. As pressure drops, the electron temperature and the heavy particle temperature can diverge, and the arc becomes more non-equilibrium. A large body of established literature anchors this thermal arc picture, including the survey by Fink-Hellenberg and Mecker in 1956 and the review by Pfender in 1978. Within that literature, arcs are distinguished from other discharge modes by 3 principal features. For simplicity and clarity, the discussion is restricted to steady-state direct current arcs, where the baseline mechanisms are easier to isolate. This sets up the later modeling and stability discussion by first pinning down what regime is being assumed and where the assumptions break down. An arc is a high current density discharge, and that intensity becomes most extreme at the electrodes. The current density in the arc column can exceed 10 to the 6th amperes per square meter. That number matters because it is not a small increment over other discharges. It is a different regime of energy delivery into the plasma, with much stronger Joule heating and stronger coupling between the electrical circuit and the thermal state of the column. The comparison baseline is the positive column of a glow discharge. Typical glow positive column current densities are around 10 to 100 amperes per square meter. So even before looking at electrodes, the arc column already sits orders of magnitude above the glow regime. Then the electrode attachment makes the contrast even more pronounced. An arc can attach to an electrode, especially to the cathode, as tiny spots rather than as a broad uniform contact area. When the same current is forced through a very small attachment area, the local current density can rise dramatically, reaching about 10 to the 10th amperes per square meter in those cathode spots. That localization immediately translates into extreme thermal loading. The associated heat flux densities can sit around 10 to the 9th up to 10 to the 11th watts per square meter. At those levels, the electrode is not just getting warm. Without design precautions, the electrode can lose mechanical integrity through melting, erosion, cracking, or structural weakening. So the practical engineering consequence is straightforward. If a device relies on arc attachment at electrodes, the electrode design and its cooling, materials, geometry, and attachment control must be treated as a primary reliability problem, not as a secondary detail. As indicated in Figure 1, the potential distribution in an electric arc changes very rapidly in front of the electrodes. That rapid change creates the electrode fall regions, namely the cathode fall and the anode fall as shown in Figure 1. The cathode fall is the key point of interest because it highlights a major difference between arcs and glow discharges. For an arc, the cathode fall is around 10 V, whereas glow discharges typically show cathode falls above 100 V. This relatively low cathode fall follows from more efficient electron emission mechanisms at the cathode in an arc. When interpreting Figure 1, the electrode region thicknesses dC' and dA' are drawn enlarged, especially when high-pressure arcs are discussed. For the same reason, the labeled Vc' in Figure 1 does not generally represent the true cathode fall. The actual cathode fall Vc, corresponding to the electron space charge region in Figure 1, can be several volts lower than Vc'. Even if the overall arc voltage in a given discharge vessel is lower than that of a glow discharge in the same vessel at the same pressure, the total voltage drop is not a reliable criterion. Depending on arc length and the energy balance of the arc column, the overall voltage drop of an arc can still be very high. At sufficiently high pressure, column brightness becomes a reliable way to tell an arc apart from other discharge modes. The key requirement is pressure P at or above 1 kPa. Pressure matters because it sets the gas density, and gas density controls how often particles collide. More collisions make it easier for electrical energy to transfer into the gas, producing strong excitation and light emission that a human eye can clearly notice. In the high-pressure thermal arc regime, roughly P at or above 100 kPa, the arc column can become extremely luminous. Thermal arc means the plasma is strongly heated and behaves closer to a thermalized state than low-pressure discharges. In simple terms, the arc column becomes a very bright, concentrated light source because excited atoms and ions relax and emit radiation efficiently under frequent collisions. This is why the luminosity criterion works as a discriminator only when pressure is sufficiently high. At lower pressure, electrons and heavy particles can be at very different temperatures, collisions are less frequent, and brightness can drop or behave in ways that do not track the discharge mode cleanly. So brightness alone stops being a dependable label in low-pressure conditions. Because the column luminosity becomes extremely high in high-pressure thermal arcs, the same property is directly useful in practice. The illumination field is an obvious example, where the arc column's intense light output is exploited in high-pressure arc lamps and related light source technologies. Cathode and anode regions can be treated as thin boundary layers that sit directly on top of the electrodes. These boundary layers are where the most abrupt electrical changes happen, because space charge can exist right in front of the surfaces. Figure 1 highlights that contrast by separating the electrode-adjacent fall regions from the arc column itself. The arc column forms the main body of the arc and typically has a comparatively small potential gradient. Potential gradient is simply how fast the electric potential changes with distance. A small potential gradient means the column does not need a steep voltage slope per unit length to carry the imposed current. Unlike the electrode-adjacent regions, the arc column behaves like true plasma where quasi-neutrality prevails. Quasi-neutrality means the densities of positive and negative charges are nearly equal, so the net charge is close to zero over most of the column volume. That is why the column is often modeled with plasma transport and energy balance ideas, while the electrode boundary layers require special treatment for space charge and emission physics. Pressure in the arc column is usually uniform and essentially equal to the surrounding fluid pressure. A notable exception appears at extremely high current levels, I greater than 5,000 ampere. In that regime, the current generates its own magnetic field, and the interaction of current and magnetic field produces an inward magnetic force. This magnetic squeezing is the pinch effect, and it creates a radial pressure gradient that raises the pressure on the arc axis. For a given arc current, the column does not keep an arbitrary internal state. The temperature distribution and the associated thermodynamic and transport properties adjust until the required field strength to drive that current is minimized. This is the Steinbeck minimum principle, referenced as Peters 1956. A relatively small field strength in the column can also be viewed as a consequence of a favorable energy balance, largely governed by the charge-carrier balance. Charge carrier balance refers to how electrons and ions are created, lost, and transported, which strongly influences conductivity and therefore how much electric field is needed for a given current. A clean way to understand how an arc column sustains itself is to zoom in on a small piece of the column and treat it as a control volume, as in Figure 2. A control volume is an imaginary boundary you draw around a small region so you can write balance laws: what comes in, what goes out, and what is created or destroyed inside. Inside Figure 2, the applied electric field E pushes charged particles into a net drift. Drift means a small average motion superimposed on random thermal motion. Both electrons and ions drift, but electrons usually dominate the current because they are much more mobile than ions. Mobility is the ease with which a particle accelerates and responds to an electric field while colliding with the background gas. Because electron mobility is far higher, the ion contribution to the total current flow is often negligible compared to electrons in the arc column. Steady state in Figure 2 means no net accumulation inside the control volume. For electrons, the same number entering through surface A per unit time must leave through surface B. For ions, the same idea holds but with the flow direction reversed. That simple through-flow picture is not the whole story, because charge carriers also leak out sideways. Across surface C, electrons and ions are continuously lost by ambipolar diffusion. Ambipolar diffusion is a coupled diffusion process. Electrons and ions diffuse together to preserve quasi-neutrality, rather than separating strongly. Outside the control volume, those escaped charge carriers recombine, meaning electrons and ions meet and neutralize. When charged particles diffuse out through surface C, the plasma loses charge carriers. To keep steady state, the arc column must replace those lost carriers inside the control volume. That replacement requires ionization of neutral particles at the same rate as the loss. At the same time, neutral particles diffuse in the opposite direction to maintain mass balance in the control volume. Cooling at the arc fringes changes that balance in a counterintuitive way. If convection enhances cooling near the edges, the temperature gradient becomes steeper, and the charged particle density gradient also becomes steeper. Steeper gradients drive stronger diffusion, so charge carriers are lost faster across surface C. To compensate, the control volume needs a higher ionization rate, and that typically demands a higher field strength E. With the current I held constant, increasing E increases the energy dissipation per unit length, IOE, which raises the core temperature of the arc column. So stronger fringe cooling can lead to a hotter core when the current is fixed. A final caution is that charge carrier losses are only part of the full energy picture. The actual E or power dissipation is determined by the entire energy balance, including heat conduction, convection, and radiation losses. Ionization in an arc column is usually dominated by electron impact, meaning an electron collision provides the energy needed to ionize a neutral atom. In high-pressure arcs with P greater than 10 kPa, the mean free path E of an electron is short because collisions are frequent. That short mean free path limits how much kinetic energy an electron can gain from the field between collisions. EQ 1 expresses this limitation: E, 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 I. Here E is the elementary charge, E is the mean free path length, E is the field strength, and EI is the ionization energy. The inequality states that even in the most favorable case, the energy gained from the field over one mean free path is much smaller than the ionization energy. In that situation, charge carrier production must rely more on thermal ionization than on direct field-driven acceleration. Only the high-energy tail of the Maxwellian electron energy distribution has enough energy to make ionizing collisions. Arc column behavior can be computed in principle by solving the conservation equations, but only after two hard prerequisites are met. The thermodynamic state must be known, and the transport coefficients must be available. Transport coefficients are the material properties that convert gradients into fluxes, such as electrical conductivity, viscosity, thermal conductivity, and diffusion coefficients. Even if local thermodynamic equilibrium is assumed inside the arc column, realistic boundary conditions remain a major obstacle. Boundary conditions encode how the plasma interacts with electrodes, walls, and inflow or outflow, and these interfaces are exactly where many non-ideal effects concentrate. On top of that, the governing equations form a coupled set of nonlinear differential equations, which is mathematically stiff and computationally expensive. Because of those constraints, the standard strategy is to introduce controlled simplifications. A simplified model rarely reproduces the exact arc column behavior, but it often exposes trends that stay valid across many operating conditions. The historical starting point is Ellenbos 1935, which treated an arc column in an asymptotic equilibrium flow regime. That regime decouples the energy equation from the momentum equation, and from the energy point of view it becomes equivalent to the no-flow case. This decoupling is valuable because it isolates thermal balance without needing the full momentum coupling to extract first-order behavior. Figure 3 ampere then provides a key existence constraint through electrical conductivity, sigma. For argon, hydrogen gas, and nitrogen gas plasmas, the column cannot exist below sigma about 10 cubed ampere/Vm, which corresponds to temperatures around 700 to 800 Kelvin. The same lower limit also applies to argon and hydrogen gas and argon/helium mixtures, at least when the helium content is below 90 vol% helium. Helium-rich cases behave differently. For pure helium, or mixtures above 90 vol% helium, the minimum temperature for sustaining the column must exceed 11,000 Kelvin. Figure 3 ampere also shows a saturation-like trend. Sigma does not change much above about 13,000 to 14,000 Kelvin. That plateau matters because once conductivity stops increasing, raising temperature further stops being an efficient way to reduce electrical resistance for a fixed current. Figure 3b adds a gas-dependent severity ranking via the heat flux potential. For argon, nitrogen gas, and hydrogen gas, Figure 3b indicates that constriction becomes most severe for hydrogen gas, less severe for nitrogen gas, and least severe for argon. This ordering is a compact way to anticipate which gases will demand more aggressive stabilization or cooling management for the same current and geometry. Figure 4 frames a practical upper limit for temperature in a hydrogen arc by focusing on the axis, where the arc core is hottest. The quantity on the vertical axis is the highest feasible on axis temperature T, measured in Kelvin. The horizontal axis is the power input per unit length, a power density along the arc column that captures how aggressively energy is deposited into the plasma per axial distance. Both axes are shown on logarithmic scales, so equal spacing corresponds to multiplication by 10, not addition. A rising curve on log axis signals a scaling rule. Increasing power per unit length raises the feasible peak core temperature, but the gain per decade can change across the range. Figure 4 also separates a theoretical envelope from experimental observations. The theoretical curve extends to higher power densities and indicates how high the on-axis temperature could be in an idealized setting. The experimental points sit lower and span a narrower range, reflecting practical constraints that reduce achievable temperature. Those constraints typically include radiative losses, heat conduction to cooler regions, convective mixing, and boundary interactions that are not fully captured by simplified theory. The key engineering interpretation is to treat Figure 4 as an envelope for design decisions. The curve provides a ceiling for axis temperature at a given power per unit length, and the experimental band indicates a more realistic operating region. Axis temperature is a peak value, not a cross-section average, so average plasma temperature and near-wall temperature can be substantially lower. For hydrogen plasma torches and arc gas heaters, Figure 4 provides a compact sizing relationship. Increasing power per unit length pushes the core hotter, while loss management determines how close operation approaches the feasible envelope. Figure 5 captures a practical arc configuration that matters far more in engineering hardware than in a quiet laboratory setup. A wall-stabilized arc operated with a strong superimposed gas flow. The core idea is stabilization by geometry and cooling. Instead of letting the arc column wander freely, the arc is forced to live inside a cooled channel made of many short, cascaded segments. That cooled wall acts like a physical constraint, shaping the column and making the arc behavior more repeatable. Axial flow is the second lever in Figure 5. Plasma gas is driven from the cathode side toward the anode side, passing through an entrance region and then a fully developed region. Entrance region means the flow and temperature fields are still forming and adjusting. Fully developed region means the profiles have largely settled into a consistent shape along the axis, which is valuable for analysis and for applying scaling laws. Laminar flow is emphasized because it is orderly and predictable, so it supports cleaner comparisons when power, geometry, or flow rate is changed. Water cooling shown in Figure 5 is not a minor detail. Water in and water out represent active heat extraction along the wall. That heat extraction sets the wall temperature boundary condition and strongly influences column constriction, heat transfer, and the stability of the arc column. In arc gas heaters, the whole point is controlled energy transfer into the flowing gas, so the coupling among gas flow, wall cooling, and electrical power is the central design problem. The reason the wall-stabilized cascaded arc with laminar axial flow receives special attention is the opportunity to apply scaling laws. Scaling laws are simplified relationships that let a designer predict how key outputs change when size, flow, or power is scaled up or down. A stabilized, repeatable geometry plus well-characterized flow makes those relationships more trustworthy than in free-burning arcs. A critical caution is embedded in the way Figure 5 is drawn. Figure 5 assumes the arc attachment at the anode is fixed and rotationally symmetric. Real arcs do not behave that politely. The arc root typically moves continuously over the anode surface, which redistributes local heat flux and changes erosion patterns and stability signatures. So Figure 5 is a useful oversimplified map of the hardware and the intended operating concept, but realistic modeling and diagnostics must treat anode root motion as a key non-ideal effect.